So as we have a nucleus, inside the nucleus we have neutrons and protons, and around the nucleus we have electrons revolving around in a region called shell or orbit. The size of the nucleus is very small, and the forces which are acting within the nucleus on the particle, that is called a strong nuclear force. A strong nuclear force can be attractive, it can be repulsive. So basically how this strong nuclear force is acting, example, you have two protons within the nucleus. If these two protons are moving away from each other, so what this strong nuclear force will do, it will try to pull them back towards each other. So the direction of strong nuclear force is to pull them back so that they will remain intact with each other, like remain closer to each other so that they will not leave the nucleus. And what happens when the two protons are coming towards each other? If the two protons are moving towards each other, what will happen in that case? This strong nuclear force will try to push these new two particles so that they will not collide with each other, try to push them away from each other. So a strong nuclear force can be attractive, can be repulsive, and it is continuously changing its nature, because the main purpose of this strong nuclear force is to bind the nucleons, to keep these nucleons inside the nucleus so that they will not escape. So to apply, so there is some energy is used to apply this force, but how this energy is present, this energy is actually the known as the binding energy. And how we will find, like how or what will be the binding energy, how to calculate this binding energy? So the binding energy, it is energy required to hold the nucleons inside the nucleus. So what is the origin, how, from where this energy is coming? This energy, the origin is the mass defect. What is the meaning of mass defect? Like example, you have two protons and two neutrons. So origin of the binding energy, the origin of the binding energy is the mass defect. So binding energy, it is energy required to bind the nucleons within the nucleus. Now, from what is the origin of this binding energy? Example, we have two protons and two neutrons. which are outside the nucleus. So when we find the mass of these particles independently outside the nucleus, example, the mass is equals to 4. This is just, I'm taking an example. The mass is equals to 4. Now, if these particles are present in the nucleus, when we measure the mass of the nucleus, the same particles, same number of the particles, when we measure their mass inside the nucleus, we find that there is difference between the mass when the particles are independently outside the nucleus and same number of particles inside the nucleus. The mass of the nucleus is coming out less than when they are independent. So what is the reason? What happened to this mass? Basically, this mass is converted into energy, and that energy is used to bind the nucleon. So we will find the mass defect, and using a mass defect we can find how much energy will be there used to bind the nucleons. Is it clear, the concept of the mass defect and the binding energy? The origin of this binding energy and mass defect? So when we calculate the difference of the mass of particles outside independent compared to the mass of the nucleus, we will find there is always a difference, and that difference is known as a mass defect. And mass defect multiplied by speed of light square will know how much energy will be there to hold these nucleons inside the nucleus, and that energy is known as the binding energy. And what is the binding energy per nucleon? Binding energy per nucleon, the binding energy per nucleon means how much energy is required to bind each nucleon. So the total binding energy divided by number of the nucleons, the number of the particles inside the nucleus, will get the binding energy per nucleon. If we sketch a graph for binding energy per nucleon, what we will find, the shape of this graph of binding energy per nucleon. This is the shape of the graph for binding energy per nucleon. So maximum value of binding energy per nucleon, what you will find for iron. So it means in terms of nuclear stability, iron is the most stable nucleus. In terms of nuclear stability, it is about 8.8 mega electron volt per nucleon. So how to get the mass? First we'll find the mass defect, like mass of particles outside the nucleus, mass of the nucleus. When we take a difference, we'll get the mass, and then that divided by the number of the nucleons, we'll get the binding energy per nucleon. So the graph shows that iron is having the highest binding energy per nucleon. Other particles are there, but they have lower than iron. That is also a reason why you will find that the heavy nucleus will undergo nuclear fission and the lighter nuclei undergo nuclear fusion. So what is the reason? Because they want to get stability, they want to reach a nuclear stability, and they can reach this nuclear stability once they have the highest binding energy per nucleon. So the characteristic of this graph also explain a reason why the lighter nuclei undergo nuclear fusion and the heavy nucleus undergo nuclear fission. Because for heavy nucleus, it has to reduce the atomic number. How it can reduce the atomic number? By breaking down into smaller one. For lighter one, they have to increase the atomic number. So how they can increase the atomic number? By fuse together and result in a formation of a heavy nucleus. So nuclei, what is the characteristic of this one? Nuclei near the peaks of the curve are the most stable, like which you will find here. They are the more stable nuclei as compared to others. The curve peak at iron, which is 56, so it shows that iron is having the highest value. The graph for binding energy per nucleon against the nucleon number is also in a similar inform, like same identical way it shows. And how we can relate a nuclear process and the binding energy. Like example, the process such as radioactive decay. What is a radioactive decay? Radioactive decay means the nucleus is unstable to hold the heavy part, like so many nucleons are inside, and the nucleus is unstable to hold these particles, so it start to emit out the particles, the energy, and we call that as radioactivity. The spontaneous and random emission of radiations by unstable nucleus, this is known as radioactivity. So why the nucleus is unstable? Because there are a lot of nucleons. I'm just drawing this as a nucleus. This is not the atom. There are a lot of nucleons inside. So naturally, when element is having atomic number more than 82, they are radioactive. Why they are radioactive? Because lot of particles are there. The nucleus is not able to hold them together. So how the nucleus get its stability? By increasing its binding energy. And how it can increase its binding energy? Because we have the formula binding energy by making it more binding energy per nucleon. So what happened? The binding energy divided by number of the nucleon will get the binding energy per nucleon. So binding energy is there, but now as the number of the nucleon decreases, the binding energy per nucleon will increase. That's why the radioactive nuclei or radioactive atoms start to emit the particles and radiation. When two protons and two neutrons are coming out, we call that as alpha. When electron is coming out, we call that as a beta. And when energy is released by the nucleus, we call that as gamma. So if the nuclear fission and fusion also involve like nucleon be rearranged in a different nuclei. So if the new nucleus is produce a higher binding energy per nucleon, the energy is given out, and all spontaneously occurring process involve energy is being given out. So alpha is 2 proton, 2 neutron, beta can be positive beta, it can be negative beta, and gamma is only emission. So if it is alpha emission or alpha decay, if we have a radioactive nuclei, when it emit out alpha particle is also known as a helium nuclei. The nucleon number or the atomic mass will decrease by 4, and the atomic number will decrease by 2, and because the atomic number change, the whole atom will change. For a beta decay, if there is a beta emission or beta decay, beta it's of two types. It can be a positive beta decay, it can be a negative beta decay. So what happened in a negative beta decay? Negative beta decay means that electron is emitted out. And what happened in a positive beta decay? A positive beta decay, it means positron is emitted. So the general equation, you have to learn the general equation for both. Positive is a positron. So what happened, like example, in a negative beta decay, a neutron breaks into proton, electron, and anti-electron neutrino. Why there is anti-electron neutrino? Because otherwise, if there was no anti-electron neutrino, the lepton number will not be conserved. But in a positive beta decay, what happened? A proton break down into neutron, a positron, and electron neutrino. For each lepton, the lepton number is +1, and anti-lepton it is -1. So the electron neutrino and anti-electron neutrinos are to conserve the lepton number. So if I write a general equation for negative, if any element is there, A and Z, converted into a beta, emitted out a beta, negative or electron, the nucleon number will not change. Why nucleon number will not change? Because the neutron number decreased but the proton number increased. Nucleon number is a sum of neutron and proton. So one is decreasing, other is increasing. Nucleon number will not change. What happened to proton number, the atomic number, because proton number increased, so atomic number will increase by 1. And in a positive decay or beta decay or a positron emission, the nucleon number, because proton decrease, neutron increase, so net sum will remain same. That's why there's no change in the nucleon number. But atomic number, as the number of the proton decrease, atomic number will decrease by 1. And for gamma, gamma is actually not, there's no change in atomic number or atomic mass. Gamma is emission of electromagnetic radiation. So when you have a radioactive nuclei which is unstable, vibrating, so when it vibrates, it release energy, and that is known as gamma. So we have alpha, we have beta, and we have gamma emissions. And when we say a radioactivity is a spontaneous and random, so spontaneous means there is no external conditions can affect this change. And random means there is no order. So there is no order for this, like first radioactive element emit alpha, then it emit beta, then the third one it can emit gamma, or it can again emit out alpha. And spontaneous means the external factors such as like temperature is there, pressure is there, the state of the substance, these all are not affecting the emission of these radioactive radiations. Then we have a nuclear reaction. There are two nuclear reactions, fission and fusion. So we have nuclear fission reaction and we have nuclear fusion reaction, nuclear fission reaction, when the heavy nucleus break down into a lighter one by the help of a neutron, and it should be a slow neutron, not too fast. Why? Because if it is too fast, maybe it will pass from one end to another. That's why it should be a slow neutron, and when the slow neutron enter to this nucleus, it will reduce the binding energy per nucleon. Why? Because now number of nucleon increase, so binding energy per nucleon decreases. To gain the stability, this nucleus will break down into lighter nuclei and emit out more neutrons. That is why the fission reaction is also called a chain reaction. Why we call fission reaction as a chain reaction? Because these neutrons which are emitted out, they further collide with more heavy nucleus and multiply this mechanism which process and further release more neutrons, and the radioactive smaller nuclei which is having a more binding or higher binding energy per nucleon. So nuclear fission reaction is a chain reaction which multiply, which increase or enhance. So it should always be a control reaction. When we carry out a nuclear fission, it should be a control reaction. So as you can see in this, you have a you have uranium you target by a neutron. This uranium, because the binding energy per nucleon decreases as one neutron is added, it will dissociate into lighter and release further 3 neutron. And these 3 neutron multiply and the further reaction will go on. Now for this purpose, what we use a moderator. Basically what the moderator is doing, moderator is changing the speed of these neutron. For to be or to use a moderator, we can also use a hard water. A hard water can also be used for the moderator, because what happened, naturally occurring uranium, when we have a naturally occurring uranium, it's about only one atom of uranium 235, and most of them are 238, and 238 required more energy as compared to 235. So average naturally occurring neutron from a fission reaction, usually they have energy between the two. So therefore a nuclear reactor moderator is used to slow down this. And to use as a moderator, we can use a graphite or we can use a heavy water. What is the meaning of heavy water? Heavy water means which contain a isotope of hydrogen, hydrogen 2 1 or deuterium, that's called a heavy water. And after that we have a control rod, because this should be controlled fission. Otherwise, if multiplied, and one fission is releasing a small amount of energy, but the process is multiplied, as a result it will give lot of energy. So it should be a controlled one. And for controlled fission, what we use these control rods. And how we use a control rod, it can be a cadmium or a boron rod. So how we can control this? By removing the energy or stopping these neutrons. So if we are able to stop these neutrons for further fission, we can stop this fission or control this or rate of the fission. So for that purpose, we use cadmium or boron. And a coolant is also used. What is the purpose of the coolant? Because it is releasing energy, the temperature of the nuclear power station might increase too much and it can reach a meltdown. So to avoid meltdown, we use a heat exchanger or a coolant which remove the energy. And a fuel rod which are having a uranium normally 235, which is increased to 3%. Enrichment means like increasing the proportion of, there is a technique which is used to increase the proportion of uranium 235 in a sample, and we call this technique as uranium enrichment. And there should be a thick concrete shielding for that act as a barrier to stop any neutron from escaping, and typically it's about 5 meter. It is able to stop these neutron, beta particle, or these harmful radiations. What are environmental hazards associated with the nuclear reactors? Example, if radioactive gases or dust escape into the atmosphere, that can readily absorb by human, and it can enter the food chain. And the fuel rod which are radioactive, as a because what happened, once we use the uranium we cannot use that again, but still the uranium dissociate or break down into further radioactive element, so this can remain radioactive for a longer period of a time. For that purpose we use these we have to dispose of this nuclear waste in normally in a barren land or a desert. What are the benefits of this? A great deal of energy is produced in a small amount of fuel, and a fission does not produce any gaseous waste such as like global warming can be not be there because of this, and suitable fuel is not in short supply as fossil fuel. Like example, what happened? You can have a nuclear fuel for a longer period of a time as compared to the fossil fuel. And what happened in a nuclear fusion reaction? In a fusion reaction, the lighter nuclei join to form the heavy. When the lighter nuclei join to form a heavy, they release energy. Both reactions are exothermic. So when they release energy, that energy can be used to convert water into steam and then to rotate the turbine and produce electricity. But practically, nuclear fusion reactors, small scale can be done, but for large scale, it is not possible to have the fusion reactors. The reason is that because for fusion reaction, you have to fuse the two nuclei. So possibly what happened to fuse them, you have to, there are neutrons and protons, like charges are there. So you have to overcome this repulsion. To overcome this repulsion, you have to apply a greater amount of force, or you have to supply greater energy. Input energy is more, but as a result, when it occur, it release enormous amount of energy. One fusion release more energy as compared to one fission. But there are practical difficulties of building a nuclear fusion power station as compared to fission. Small scale can be done, but large scale it is not possible. Reason for that, as you can see, the fusion reactors, it is much more difficult to achieve and control the fusion than fission, because it is, you have to overcome the repulsion between the nuclei, and that required a very high temperature, about 100 million Kelvin or above. A normal container cannot hold anything as hot as this. But what are the advantages? A fusion has a number of advantages. It is more productive energy source than a fission per kilogram of material. Raw material of a fusion can be obtained from seawater as well. Like we need hydrogen for that. Hydrogen fused together to form helium. And the waste product are not radioactive, and uncontrolled chain reaction cannot develop. So you don't have to, like, uncontrollable chain. Some of the fusion are chain, but it's not like long chain, only like 4 or 5 steps and then it will stop. So when we compare them, however, a controlled nuclear fusion is very difficult to maintain. What is the reason? The kinetic energy needed for the two positively charged to come closer to each other, that is, so you have to supply high temperature for that to overcome that. And to have a sustainable reaction, proton must have enough collision frequencies. Yeah, definitely these reactions, even a fission or a fusion, will stop once we have iron. And the presence of the iron in on Earth as well as in the outer space shows that they already undergo a nuclear reaction. And if we don't want the proton to touch the wall, so if the temperature falls, the fusion stop. So hence to stop it by a strong magnetic field is required. Like magnetic field is required to maintain or so that proton does not touch the wall of the container, otherwise they will lose energy and this will stop. And this is the part which explains the idea for binding energy per nucleon. The binding energy per nucleon. So as you can see in this part, a nuclear fission involves a heavy nucleus such as uranium and splitting into smaller nuclei, and some neutron nuclei will produce, like will move towards the peak in the graph. So energy is released and fission can only occur with a nucleus right on the peak. And fusion involve a smaller nuclei joined together to form a larger one, and fusion can only occur a nuclei on the left of the peak of this binding energy per nucleon graph. And radioactivity, the radioactivity is random or spontaneous disintegration or dissociation of the nucleus. It is a random process. And if we sketch a graph for the number of the radioactive nucleus with respect to time, it's an exponential change. So if we have number of nuclei and the time, in the beginning we have maximum, with the passage of the time it is decreasing. So exponential change is there for the number of the radioactive atoms present. The equation which relate this graph, it is similar to that. So you have n is equals to n naught e raised to the power minus lambda t. So n is equals to n naught e raised to the power minus lambda t. This is the equation which relate the number of the nuclei in the beginning, that is the maximum in the beginning, and after some time, that is n. What is lambda? Lambda is called a decay constant. Like how many radioactive atoms are decaying, and how we can work out this formula. If you want to drive this formula, the activity, the term activity means that rate of decay or the dissociation or breakdown of the nuclear. This can be number of the nucleus or it can be in activity as well. So we can say activity is directly proportional to the number of the nucleus present. Higher activity means more atoms or nuclei are present. Lower activity means less are present. Greater the number of the nuclei, greater the number of dissociation. So I can simply say L is proportional to the original number. When we replace the proportionality sign, we replace with equal to and constant. So it is lambda and n naught. N naught is the maximum number and A is the activity, lambda is called a decay constant. And activity is number of the d by dt of n, means rate of change of radioactive nuclei, lambda and n naught. So when we solve this equation, we'll get the last function n is equals to n naught e raised to power minus lambda t. So this is important. N naught is a maximum number, n is a number of nucleus present at certain time interval. Lambda is a decay constant vary from element to element, and T is a time interval for which we are finding. Then what is a half-life? Half-life means time taken by half of the radioactive nuclei to disintegrate. So n is equals to n naught e raised to power minus lambda t. After half-life, this n will be half of the original value. So I can now say it will be n naught by 2 e raised to power minus lambda and t. N naught will cancel with n naught. So it will be 1 by 2 e raised to power minus lambda t. To remove this exponent, I'll take ln both sides. So it will be ln 1 by 2 or 0.5, and ln will cancel with these, so it will be minus lambda t. When I will take the value of ln half or ln zero point 0.5, it will come out 0.693 negative, and that is lambda t. But this T is not the normal T. This is a half-life time taken by half of the radioactive atoms to disintegrate. So when I solve this, the T half or half-life time is equals to 0.693 divided by lambda. So it means if any element is having a higher value of a decay constant, it will have a short half-life. If it is having a smaller value of a decay constant, it will have a greater half-life. Is it clear? The half-life is a time taken by half of the radioactive sample to disintegrate or decay. So next session we will do the questions related to nuclear reactions, the calculations especially from the past paper. So this was about the theory part related to nuclear physics. Any question or a doubt related to the class today? This week I will share a Unit 5 homework. Alternate weeks I will give you a homework. So this week you will have a Unit 5. I will send on the group. For Unit 5, because still we have some topics such as gravitational field, cosmology, astrophysics. Questions you will leave related to those topics. Rest you will solve. I will mention in the homework which topic, which questions you will solve.